Hey guys, I'm Nihar Maheshwari, and today I'm bringing to you some really nice problems in probability. So let's get started. All right, so here's the problem statement. You can read it yourself. I'll read it out loud. Imagine that you run an electronics store with n products of a brand P. The probability of buying a certain product is P sub 1, and if a customer buys a certain product, the probability of purchasing an extended warranty that's associated with that product is P sub 2. If a customer comes by the shop and bought K extended warranties, then what is the expected number of products purchased? What is the correlation coefficient between the number of products and warranties? Comment on the behavior of the correlation coefficient for different values of P sub 1 and P sub 2. All right, cool. So just looking at this problem, we can see that we're trying to model a store with a binomial distribution of sorts. So just looking at this problem, you're seeing, okay, so this is probably from the chapter or from the topic that we call discrete joint distributions. So before you do anything, before you put pen to paper and start doing calculations, you need a basic setup. So let's get that down. Let's get some notation down and try to express our goal mathematically. So I'm denoting capital X as the random variable for the number of products purchased and capital Y for the number of warranties purchased. The goal here is to calculate the expected value of X given Y equals K. Basically, we're trying to find a conditional expectation. And in order to do that, we probably are going to need to find the conditional PMF of X given Y. Meanwhile, what information do we already have? Well, we had some information over here. We were given that, okay, X over here is distributed binomially, right? Because you can see that the probability of buying a certain product is P sub 1 and that there are n products of that type. And this probability is not changing. So you can see that X is distributed binomially. On the other hand, you're not so certain about Y because you're given that if a customer buys a certain product, the probability of purchasing an extended warranty is P sub 2. So in a way, you're kind of given some conditional information here, right? So you think that, okay, maybe I can try figuring out the conditional PMF of Y given X. What I mean by this is that suppose that you've bought, let's say, X products. Right. So if you have bought X products, I am telling you that out of these, the probability of you purchasing Y warranties for these X products is going to be binomially distributed with parameter P sub 2. And the number is obviously X, the number of items available to you. And that's exactly what we have here. We've written f sub x as the marginal PMF of x is binomial, and the conditional PMF of y given x is also binomial. This was, I think, the trickier part. And note one more thing here, that x is always greater than or equal to y. That's the only thing that makes sense because obviously you're going to buy an extended warranty only if you buy the product. Otherwise, there's no point to the warranty, right? So the number of products obviously always has to exceed the number of warranties that you buy. Anyways, so now that we know the conditional PMF and the marginal PMF, we can multiply them together to obtain the joint PMF of X and Y. And you can probably write it out easily, multiply the two out. There's actually a very interesting interpretation because you can see that when you multiply these two, you get n choose X and X choose Y. So you can probably cancel out an X factorial, right? So you do that and you do some rearrangement and you actually get this form n factorial divided by n minus x factorial y factorial and x minus y factorial. So you can see over here that in the denominator, the sum of these three factorial arguments is actually summing up to the numerator n. And you might be wondering, okay, wait, you've probably seen this somewhere. You've seen this when you were studying joint PMFs of discrete variables, namely the multinomial PMF, in which it's something of the form n factorial by x1 factorial, x2 factorial, x3 factorial, where x1 plus x2 plus x3 is equal to n. And then you have some probability 1 raised to power x1, probability 2 raised to power x2, probability 3 raised to power x3. A natural generalization of the binomial PMF, right? And you're absolutely right. That's exactly what this is, except in a slightly different form. Because see, note here that imagine that you have a product sitting there on a shelf, right? Now there are three things that can happen to it. The first thing is that the customer can go in and they can buy that product and also buy its extended warranty. So the probability of that happening is P1 times P2, right? And we've noted here that there are Y such products to which this is happening. There are Y products for which I am buying the extended warranty as well as the product itself. That's literally what it meant above here when I said Y is the number of warranties purchased. Then the second thing to note here is that another thing that can happen to this can be that you just don't buy the product on the shelf at all. The probability of that is 1 minus P1 because P1 was the probability that you buy it. And finally, the third thing is that you buy the product, but then you don't buy its extended warranty. So the probability of that is going to be P1 times 1 minus P2 because you're buying the product, so that's probability P1. And then the conditional probability that you buy the warranty when you've bought the product is P2. So the conditional probability that you don't buy the uh, warranty when you've bought the product is 1 minus P2. And you multiply the two to get the real probability. And that's why you get the second term, P1 minus P1 P2. Now let's just quickly verify if the exponents also sit correctly. So we know that there are Y warranties that are being bought. So there are Y products and warranties in case one that are being bought. In the second case, we know that there's N minus X products that are not being bought off the shelf. So they stay on the shelf, and that is literally the exponent to the power 1 minus P1. And lastly, there are X minus Y different products on the shelf that you've bought as a customer for which you bought the product but you did not buy the warranty associated with it because you got Y warranties and X products total, so X minus Y is the one without the warranties. All right, cool. So you can see that this is a multinomial distribution, and that's actually really interesting. Now, at this point, I think we should probably take a step back and try thinking, okay, what is our strategy going to be here? We figured out the joint PMF, and now we need to figure out, let's say, the conditional PMF of X given Y, right? And we know the marginal PMF of X, we know the conditional PMF of Y. So, how do we do this? Well, whenever you see that you need to sort of invert a conditional PMF, the first thing that comes to your mind should be Bayes' theorem for random variables. Namely, that fx times fy given x is equal to fy times fx given y. Because we want to find fx given y, right? So the question then arises, okay, since I want to find fx given y, I know what fx is, I know what fy given x is. How do I find out what fy is? Because if I know that, then I'm done, right? So there's a definition here that you can probably use. Fy will just be the summation of the joint PMF over all the known values of x in the given domain, right? And that's what we're going to do. But before we even get to that, let's try to just get an intuitive feeling for what you think the PMF of Y would look like. Like, what would the marginal PMF of Y look like? Well, honestly, to me, intuitively, it seems like Y will itself be binomially distributed because in the setup of the problem, we see that X is binomially distributed. There's some association probability of Y with X. So intuitively, there's a gut feeling that yes, okay, this Y is probably binomially distributed, right? But now, how do we concretize this intuition? Like, how do you build a mathematical argument of this that's soundproof and just foolproof? So, one piece of reasoning might be okay. So we know that the joint PMF of X and Y is sort of a multinomial PMF in a modified form. And we know that multinomial PMFs are only found when the individual variables are binomially distributed. Right. So that's why maybe on the basis of that alone, we can say that Y will probably be binomially distributed. But personally, I'm not very convinced. This sounds like a lot of hand waviness. And a little calculation never hurt anybody. So let's try to run through this calculation over here. Let us try to sum up this dirty expression over x equal to 0 to n. All right. So let's be sure. Okay. Cool. So you can firstly clearly see over here that when you have this expression and you're trying to sum it up, whenever you see a dirty expression of this sort and you're trying to sum it up, there should be two ideas in your mind. The first idea should be that you should try to get a binomial expansion of some sort. Because the moment you get a binomial expansion, your entire summation kind of just cleans up and you have a clear answer. And then the second idea in your mind is that you already have a goal. You already want to establish that Fy is binomially distributed with, let's say, a parameter P1, P2. So you already know that, okay, I want to kind of show that Fy is NCY times P1, P2 raised to power Y times 1 minus P1, P2 raised to power N minus Y. And with that in mind, let's try to rearrange this expression so as to get the required result. All right, cool. So look over here what I've done. What I've done over here is basically I took out the term that was not dependent on x out of the summation, and n factorial, y factorial are also not dependent, so I took them out. And then I multiplied an n minus y factorial and divided by an n minus y factorial. Now, again, if this seems like I pulled a rabbit out of a hat, the reason I did this was because I want to generate an NCY term. And that's what we'd established before as well. So I'm not really pulling anything out. Also, another reason you would probably want to get an NCY or n minus y factorial term inside the argument is because you can see that over here, you in the denominator, you have n minus x factorial and x minus y factorial. And both of these are summing up to n minus y factorial. So that's why you would get n minus y factorial over here, and you would be able to write this as a binomial coefficient, which brings you one step closer to expressing this as a binomial expansion, which is exactly what we want. Right, and then on the other hand, we have p1 minus p1 p2 raised by x minus y. Nothing remains unchanged. Everything remains unchanged here, so that will stay as is. All right, cool. So now you have n minus y c x minus y times this whole thing and this whole thing outside. Okay. Now, one thing to note here is that you'll notice this thing x equals to 0, and you'll be like, wait a second, and x equals to 0, wouldn't it be n minus y c x minus y? And that would be n minus y c minus y, and negative binomial coefficients are not defined. And you would be right, except for two things. Firstly, we already established that x has to be greater than or equal to y. Over here, we're using x equals to 0 just to show that we're trying to cover all the values of x that are in the domain from which we're mapping the sample space. And secondly, the convention that I'm going to be using throughout this video is that anything like nc negative of anything is equal to 0. Basically, whenever the argument of a binomial coefficient is negative, I'm saying that's going to be 0. Or whenever the argument of a binomial coefficient, let's say, exceeds the n, then again it's 0, because the number of ways to do that is 0. Right, I'm using binomial coefficients in the probabilistic sense over here. All right, cool. So now you can just notice over here that this is the expansion of p1 minus p1 p2 plus 1 minus p1 raised by n minus y. So p1 cancels out, and we therefore get what we predicted. And that's amazing news. Good news, indeed. Good news indeed. All right, cool. So now what's our next step? Our next step is now to write the conditional PMF of x given y and try to calculate expected value. Conditional expected value, to be more precise. So we use Bayes' theorem to do that, as we discussed before. And here we go. Ta-da! When you will have to do some cleaning up to get here. But the interesting thing to notice here, actually, is that the conditional PMF of x given y is itself somewhat like a binomial distribution. Look here. Firstly, look at the arguments of the exponents over here. P1 minus P1 P2 divided by 1 minus P1 P2 plus 1 minus P1 divided by 1 minus P1 P2. When you sum these two up, you're going to get 1, which is exactly what it looks like in a binomial distribution, ncx, p raised to power x, 1 minus p raised to power n minus x. So that's exactly what's happening. This is p and this is 1 minus p. And that's very interesting. And then the second thing you notice here is that the exponent also matches the argument, the x minus y, x minus y. And then n minus x is this n minus y minus of x minus y. So you can see that this is a sort of a modified binomial distribution that has been shifted by y with these new probability parameters. With this new parameter p1 minus p1 p2 by 1 minus p1 p2. And I think I find that very interesting because looking at the problem, I don't think it was very easy to predict that the conditional PMF of x given y will itself be binomially distributed. I don't think that was intuitive at all. And we arrived at it regardless. So now on we go to the next step, like brave men. We are going to find out the expected value of x using this conditional PMF. Okay, so note over here that I've used x belongs to d prime. The reason I am using that is because d prime instead of d is because your new conditional world will have a different domain for x. Like x can no longer be lesser than k, because if you've bought k warranties, you obviously have bought more products than the number of warranties. That's why your summation over here starts from x equals to k to n, and then you have this dirty sort of summation term here. And I don't know if you noticed, but this kind of looks like some exercises that you may have done when you were trying to evaluate the expectation of a binomial random variable. The trick that we used to use there was that we used to say that ncr is equal to n by r times n minus 1 choose r minus 1, and then we used to simplify things. And that's exactly what we're going to do here. Firstly, to make things easier, I'm going to make a substitution, which is that x is t is x minus k, so that we can start from t equals to 0 and go to n minus k. And then we divide this summation into two parts. The two parts are going to be the part that's associated with k, and then the second part will be the part that's associated with t, because I'm replacing x by t plus k over here. So then I'll distribute this by the linearity of summation. So I'll have t times this whole thing plus k times this whole thing. All right, cool. So then you can probably clearly see over here that this clearly sums up to 1. And over here, again, I use this property that NCR is n by r n minus 1 CR minus 1. I've just sketched out the rough procedure over here. I encourage you to work out the exact details yourself. Again, one thing to note here, you might be bothered by t minus 1 being here and t equals to 0 being here, but I already told you we're working with the convention that any negative binomial coefficient is defined to be 0. All right, cool. And that's when you get this really, really interesting result that n p1 times 1 minus p2 plus k times 1 minus p1 divided by 1 minus p1 p2. So the way I like to read this is that it's basically n times the probability of success in the binomial in the conditional PMF of x given y plus k times the probability of failure in the conditional experiment that we have here. Like, look at this over here. This is the probability. If I define this as the probability of success and this is the probability of failure, what you have here is you have n times the probability of success and then k times the probability of failure, which is really interesting. I think that's really interesting anyway. So moving on to the second part in which we're required to calculate the correlation coefficient. Cool. Before we do that, I think I'd like you to try an extension yourself, which is that if two customers come by the shop at different times and purchased K extended warranties, what is the expected number of products purchased by them, and how does this result generalize to M customers? So now the reason that this is particularly difficult computationally is that, for example, if we just work with the example of two customers, suppose one customer comes by, let's say X1 is the number of products he buys, Y1 is the number of warranties, X2 is the number of products the second customer buys, Y2 is the number of warranties. Then you are given that you're trying to find out the expected value of x1 plus x2 given y1 plus y2, right? And for this, you're going to need to find the conditional PMF of x1 plus x2 given y1 plus y2. So you have four random variables. You probably have some relations, like you know that fx1 will be the same thing as fx that we did before. Fy1 given x1 will again be the same. Fx2 given x1 you can figure out as well, and so on and so forth. But the thing is that this is really, really complicated, and you'll probably get your head spinning the moment you write out the joint PMF of x1, x2, y1, y2, and then try finding out the required marginal PMFs that you haven't calculated that yet, and then using Bayes' theorem to arrive at the right conditional PMF. Your head's gonna spin, genuinely gonna spin. I've done it myself. I know how it feels. So that's why I want you to instead not do that and try to think. What do you feel like the answer will be? What does your gut feeling say? And just try using the properties of expectation to arrive at an answer. I will leave that up to you. All right, cool. So yes, determining correlation. I think I've not written anything particularly difficult on this slide. I have the coefficient definition over here, which is that rho of x comma y is covariance divided by sigma x sigma y, where sigma x and sigma y denote the standard deviations of the marginal PMFs of x and y respectively. Okay, so we know that sigma x will be np1 times 1 minus p1 because it's binomially distributed with parameters n and p1. Similarly, y will also be the same thing, np1 p2, 1 minus p1 p2 because it's got parameters p1 p2 and n. And finally, you can find out covariance using expected value of xy minus expected value of x, expected value of y. You know expected value of x is going to be np1, expected value of y is going to be np2. So ultimately, the question just boils down to finding the expected value of xy. Right. So in order to calculate the correlation coefficient, you need to find out the expected value of xy. That's it. So the question arises, okay, how do you do that? Again, you need to be a little bit careful here in terms of how you're going to do this. Like, you know that the argument of your summation is going to be xy fxy, but you need to be careful about the index of summation over here and what your limits are. So we know that y can only vary from 0 to x because the number of warranties cannot exceed the number of products that you're buying. That's why the upper limit on y is given here as x, whereas x can vary anywhere from buying zero products to unproducts. It's the customer's wish, right? Like their wish. Anyways, so what I did here then is that you can write out fxy from before and distribute it in such a way so that you take out all the terms that are independent of y outside this inner summation and put them outside. And again, you have to use the same trick as before, in which you're trying to generate a binomial expansion of sorts. And that's what I'm doing here again. So I took out the n minus x factorial term. I took out the 1 minus p1 raised to power n minus x term. I took out a lot of stuff, right? Now, here's the thing. When I had x over here, x is also independent, so I took x out, and I had y over here, right? So I had y times whatever n factorial whatever that I've put out divided by y factorial x minus y factorial. So I cancel out the y over here, and I basically just have 1 by y minus 1 factorial. And now here's the thing. Again, you look at this y minus 1 factorial, x minus y factorial. So it would be really nice to have something like x minus y plus y minus 1 in the numerator. And that's why I multiply and divide by x minus 1 factorial, because that's just intuitive to me and it should be intuitive to you too. So I multiply and divide by x minus 1 factorial. And then I notice, oh, wait, but then here's the thing. P1, P2 raised to power of y would have been the actual term here, not y minus 1. Whereas I want the exponent to be y minus 1, so I can write it as a binomial expansion, right? So that's what I did. I basically just took a P1, P2 out and wrote this as P1, P2 raised to power y minus 1. There we go. That easy. So now you notice again that look over here, and ta-da, you again have a binomial expansion. Namely, you have the binomial expansion of P1, P2 plus P1 minus P1, P2 whole raised to power of x minus 1. Whole raised to power of x. You'd think it's x, but you would be incorrect. It's actually x minus 1. The reason for that is that you actually have to notice that although you're varying y all the way from 0 to x, your upper limit is effectively x minus 1 factorial, because your binomial coefficient is x minus 1 choose y minus 1. So your the highest degree term in your expansion is going to have the power x minus 1. That's why it's actually p1, p2 raised to power of x minus 1. I hope that's clear. All right, great. And that's basically what I did. I wrote that out, and again, when you sort of add these up, what you're going to get is that you're just going to have p1, p2 sort of cancel out, and you're just going to be left with p1 raised to power x minus 1, which is a really, really clean result if you think about it. So I basically then get n p1 p2. I took out n because again I had over here an x minus 1 factorial and an n minus x factorial. So I want n minus 1 factorial, not n factorial. So I took out n, I took out p1 p2 because they're independent, and then finally you have x p1 raised to power x minus 1, 1 minus p1 raised to power n minus x. All right, cool. So now the only thing that's bothering us over here is this x. And over here we do something that's, I guess, a mathematician's favorite trick. We rewrite a 0. So over here we have x minus 1 factorial, and it would be really nice if we could like kind of reduce that term further. So that's why I write x as x minus 1 plus 1, and then I distribute the summation into two parts. So what I do here then is that I have n minus 1 factorial times x minus 1 divided by x minus 1 factorial n minus x factorial. So x minus 1 cancels out, x minus 1 factorial becomes x minus 2 factorial. And that's exactly what's written here. Now over here again, same trick repeats, which is that I now need the numerator to be n minus 2 factorial because the denominator arguments sum up to n minus 2. So I take n minus 1 common outside. And on the other hand, p1 raised to power x minus 1 is not required. I require p1 raised to power x minus 2 because this is x minus 2. So I take that outside. So I take those outside, and automatically the internal summation there becomes equal to 1. Cool. And then S2 over here will be the plus 1 divided by x minus 1 factorial. That's just equal to 1. You don't have to do any kind of modification. You can clearly see this is equal to 1. All right. So that's why, therefore, I get expected value of xy is equal to n p1 p2 times s1 plus s2. And that's exactly what I've written here. Now that I have the expected value of xy, I can actually calculate the covariance. And that's exactly what I do. There is a nuance here, and I'll get to it in a bit. So the covariance of x comma y is going to be equal to n p1 p2 n minus p1 times p1 plus 1, yada yada yada. And then you get this really clean, neat expression. Now you need to be careful about a few things over here. You need to be careful that when you are now defining the correlation coefficient, you do not want to accidentally make the standard deviations in the denominator equal to 0. You need to check that that does not happen. So just one observation before that. This covariance you can see over here is always positive. That means that x and y, the number of warranties and the number of products bought, are always positively correlated, which intuitively makes not correlated, sorry, positively, yeah, well, positively correlated. This means that basically, this does not necessarily mean that as x increases, y will also have to increase. But in this case, that will actually end up happening. Anyways, another thing to note here that this covariance will only be equal to 0 when p1 is equal to 0, or p1 equals to 1, or p2 equals to 0. And at all three of these values, actually, you will notice that the standard deviations that are present in the denominator of the correlation coefficient, they also become equal to 0. So therefore, rho x comma y is actually not defined. So that is why you have to write this statement. You have to write assuming that P1 is not equal to 0, 1, and P2 is not equal to 0. Only then can you define rho x comma y as this sort of expression, where you have rho x comma y is equal to n P1 P2 times 1 minus P1 divided by that square root. And you can clearly see over here n P1 is going to cancel out in the numerator and denominator. A square root of p2 is going to cancel out, and a square root of 1 minus p1 is going to cancel out. So that's why finally you have this really, really nice, neat expression, which is that rho x comma y is p2, 1 minus p1 divided by 1 minus p2 and p2. I really genuinely think this expression is beautiful. And now let's talk about the behavior of this correlation coefficient and see if it intuitively makes sense. So you can see here that in order to figure out how exactly what is the monotonic behavior of this, you're going to have to evaluate the required partial derivatives. And keep in mind that P1 and P2 are in the range 0 to 1, 0 and 1 excluded, right? So, firstly, the first thing to notice over here is that as P, like you can evaluate the partial derivatives yourself, but I'll just tell you. As P2 increases, rho of x comma y will increase. And this intuitively makes sense because if you remember, P2 was like the association probability between buying an extended warranty and buying the product itself. And so it makes sense that you're kind of, increasing how correlated you are, or how deep the relationship is between the warranty that a customer buys and that the number of products that a customer buys. If you increase the probability that the customer buys a certain warranty, given that he's bought a product, right? So that makes sense intuitively to me, and I hope it does to you as well. And on the other hand, the interesting thing is that as P1 increases, rho of x comma y actually decreases. It's a decreasing function of P1. And this is a little bit harder to explain intuitively but the way I think I decided to interpret it is that P1 was the probability of buying a certain product, right? So in the worst case scenario where P1 is equal to 1, where you're saying, you know what, the customer is just going to waltz into the store and buy all the products on the shelf, uh, you're saying that it does not matter to the warranties how many products it basically does not matter to the warranty how many products you buy. You're going to buy all the products anyway. It does not matter if you buy 5 warranties, 10 warranties. You're going to buy all the products anyway. So as you increase the value of P1, you're getting closer and closer to this situation